Thank you. Thanks a lot. And also, thanks so much to the organizers to put this event together. I'm very much looking forward to spending the next couple of days interacting with you all. All right, so I'm not from far from here. I'm from the University of Waterloo and IQC, the Institute of Quantum Computing. My group is called Quantum Interactions Group, and if you want to learn more about what we're doing, so you can find more information at quantuminteractions.com. So we do several things, and one of our research streams is quantum simulations of fundamental particle interactions. So it's quite interesting that in particle physics, you can have announcements like this. So it's very recent. So if you look here, that's just July this year. And the LHCb collaboration, they discovered 3 new exotic particles, which have never been seen before. So you have a theory like quantum chromodynamics, which has been known by decades, and yet new things are found. And also when tetraquarks per se were discovered, so back then it really hit the theorists by surprise. So this is a good and proper reminder that even so, if you know the basic rules, it doesn't mean you know the answers to your burning questions. Yeah? And it's really complex simulations that need to bridge the gap now between I know my model or I have the answer to my question. Yeah? And just to stress the importance of simulations just even more. Yeah, so these simulations, we really need them to figure out like our world around us. Yeah, to really see what the standard model of particle physics like really allows to understand phenomenology, like everything around us. And it gets even more interesting actually when you get to the point when your observation does not match your simulation, no? Because that's the crack where then you know, okay, now here could be new physics where we learn really something new, where we expand our knowledge and then also develop new theories. And all of these very, very important simulations are done traditionally with this theory, which I call here traditional lattice gauge theory, like you discretize space and time, use path integral formalism, and then on supercomputers, you run Monte Carlo. And this is just insanely successful. Yeah, so I'm kind of surprised because we're dealing with a truly quantum problem here. Yeah, and these are just like classical computations, so they're really incredibly successful given the quantumness of the problem. However, there are problems that are, or let's say, pockets of problems which remain inaccessible despite this amazing success. So if I talk about pockets of problems, like these pockets are like vast. Yeah. So for instance, like real-time evolutions. Like I, as a quantum optician, I would just say time evolutions. Yeah. So everything dynamical, like this is large spans a large number of problems in itself, like equally chemical potentials when I have fermions, but at a high density. And like all of those are fundamentally out of reach for this particular approach of traditional lattice gauge theory. And this is exactly what motivates, this is a motivation for exploring the use of quantum computers. Like here, going with one of my favorite quotes, which undoubtedly I have seen a million times. So if nature is quantum, goddammit, and so if you want to simulate it, we need a quantum computer. So just to wrap up this introduction, so we really need complex simulations. They are absolutely key. And they are in principle successful, but there are these huge problem classes which are currently out of reach. So therefore, we want to teach computers how to help us here. And this is a personal timeline, like from my own perspective. So here we see back in 2005, we already had very early theory proposals. So like early visionaries, like really writing, oh, you could use a quantum computer for problems in particle physics, and it's going to be different. It's going to be a different type of simulations from, say, chemistry or from condensed matter physics. And so here in 2016, we like our experimental and theoretical collaboration. We did theory, and the experiment was done in the group of Rainer Blatt. It's the first experimental demonstration of a quantum simulation in lattice gauge theory. And here is a lot of white space where a lot happened. So like really many more exciting experiments. I'm citing a review paper that we wrote here. And here at University of Toronto, you of course also have Nathan Wiebe, who also does very exciting work in this area. And he also has a white paper, which is much more recent. So if you're interested in knowing what more exciting experiments means, you could just look there. And to make a long story short, now it's a very highly active field. We have dedicated conferences, we have dedicated workshops, we have funding schemes, even special issues. So a lot of people look into quantum computing for high energy physics. So to zoom in a little bit on my personal story, so this 2016 experiment, it was a real-time evolution, so the thing that lattice gauge theory cannot do. And back in 2016, we did it, or our experimental friends did it with 4 qubits, and we simulated this on a trapped ion quantum computer for QED, for quantum electrodynamics, for electrons and positrons interacting. And then moving on to 2019, still with the same collaboration back in Innsbruck, still with a trapped ion quantum computer, but changing the approach to a variational quantum simulation with a VQE approach, and extending really the number of qubits to 20. So it was a bigger experiment. And yeah, what these 2 demonstrations really had in common, it was a simulation of quantum electrodynamics, which is one of the simplest gauge theories that you can think of. And it's a so-called abelian gauge theory. But if we want to simulate, or if you want to describe stable matter as we know it, as we see it all around us, so to give it a bit of a Canadian flavor, for instance, canoes, trees, and things like that, we really need non-abelian gauge theory. So there was an urgent need to move on, like if we want to go down this path. And this is just to drive the message home that abelian theories are nice, but also limited, because if you want to make a gauge singlet, like something that nature kindly does, like considers neutral, then you always have to have as much matter as antimatter. But of course, like this is all matter only, like we're matter only, right? And if we want to have a gauge singlet that can be built from matter only, we really need non-abelian theories. So we must be able to simulate that if we are getting serious of unlocking really the potential of quantum simulation for particle physics. So we took on this quest last year. So, yeah, it took much longer, but last year we had something to publish, where here we picked a different platform. So it was not trapped ions, it was a superconducting platform, IBM Quantum Experience to be specific. And we stuck to one spatial dimension as before. And we did a simulation with 2 colors. Of course, nature has 3 colors, but to get a start and to learn how to include color degrees of freedom, how to do non-abelian gauge theories, we started to include 2 color degrees of freedom as a benchmarking model. And here you see a plot I'm very happy about, because it shows like how 2 matter particles form a SU2 baryon, yeah, in a color singlet. Oh, and in case you're concerned that everything is in one spatial dimension, so we got to start somewhere, right? So all these demonstrations were 1D, but it was still considered to be among the top 10 breakthroughs in physics physics that year. So it's about, yeah, learning to walk before you start running. Yes, and but the journey doesn't end there, because now we know how to include color degrees of freedom. We know how to do a non-abelian gauge theory. But yeah, nature has 3 colors. So nature does SU3 and not SU2. So this is the next step of the staircase to get really to the gauge group of QCD. I mean, it's one-dimensional QCD still, but to get the gauge group right. And that is what I want to talk to you about today. Yeah, and everything is also summarized in this very recent preprint that we put out. And while I'm at it, let me give you already just a whole summary of what it's about. It's about simulating 1D QCD, like really on a quantum computer. And it's theory and experiment 2 in 1. And we simulate tetraquarks and we simulate real-time evolution. And so what is the whole point? So the whole point and significance was really to simulate quarks with 3 colors, to have non-abelian matter with the gauge group as required by QCD. And we were actually not the only ones. So there was very recently also a second preprint in the group of Martin Savage at the University of Washington, who also achieved this. But going back to the Canadian version, I was very blessed to work with this team. So yeah, it was like really a pleasure and a joy to work with those people. So here you see 3 very talented postdocs, all from IQC, University of Waterloo. Simply amazing summer student who joined us and did calculations beyond all expectations, really. And we had Sieglinde, yeah, from IBM, who helped us with the experiment. And nothing would have been possible without our particle physics collaborator, who's also here from Toronto, from York University. Okay, so this was a team, and so let's go straight into it. So here is one-dimensional space, and we're looking at lattice QCD. So we discretize space. So here is 1D space on a lattice, and we put matter on the vertices. Yeah, so for each vertex, we have now matter fields defined, and we put gauge fields, which mediates interaction in the links in between. So you see it blue here. And there's a catch. There's a technical detail that when we put our matter on our lattice, we will do in such a way that on all even particle sides, we put the particle, and on the odd sides, the antiparticle. So originally, in each point of space, we would have a 2-component spinor with matter and antimatter, but for technical reasons, to avoid the so-called fermion doubling problem, we rip the one beautiful spinor apart and put the upper part on all the even and the lower part on all the odd sides. But that's just a technical thing, and each of these boxes is in reality 1 point in space. And yeah, we have then matter fields, and we still need color. And I'm glossing over a ton of details here because I have only 30 minutes. But the bottom line is I want to simulate this on a spin qubit quantum computer, I want to formulate this in qubits. And how we do that is that we take each of the original lattice sides. So this was an antimatter side. And then we put 3 spins in order to represent the 3 colors. So the first side would be anti-red, then anti-green, and then anti-blue, and then red, green, blue. And this is one elementary cell, and then you just repeat it over and over and over again, and you have one-dimensional quantum thermodynamics. And the next point is not so important. I'm just mentioning it here that there's a translation table, like how you encode what up and down means on your quantum simulator. So for instance, if I have down, down, down here, it means vacuum, 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 and up, up, up would also mean vacuum, vacuum, vacuum. And if I would have up, 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 down, down, down the other way around, it would be like really filled with an anti-red particle, anti-green, anti-blue, red, green, blue. Yeah, but long story short, in the end of the day, you do a lot of encoding, but you end up with a exotic spin Hamiltonians that in the end of the day you can put on your quantum simulator. Except there's one more detail. One more detail is, yeah, there were the gauge fields, which matter a great deal. And the gauge fields, since we're working in one dimension with open boundary conditions, we can actually eliminate them by a gauge transformation. And this way we can get a Hamiltonian description in terms of matter fields only. So why would I do that? I do that just in order to get a more resource efficient description. So in other words, this is only done in order to use as few qubits as possible. Yeah, because like our chairman said, NISQ devices, we want something that works like now. So we use as few qubits as humanly possible. So this is why we eliminate the gauge fields. The color electric fields, they still contribute. And if you want to simulate it, by all means, go ahead. You can still do that. Like you can run your quantum simulator and plot out the electric field, color electric field distribution, no problem. So in essence, this is just to explain the resource efficiency a bit more. Like you have a big Hilbert space, which has all the gauge fields and matter fields, but this being a gauge series, a gauge invariant Hilbert space, which is like the physical states that make sense in the theory, they live in an exponentially small subspace, and I'm basically only simulating this and not the whole thing. And like we have more work on this, which I'm referencing there. And in the end of the day, you have now your encoded spin Hamiltonian, which has 3 parts. So you have here a term which gives you the kinetic field energy. You have a term which gives you a term which describes the bare mass, and you have a term which charges you for the energy stored in the color electric field. And yeah, the Hamiltonian looks a bit complicated. So I didn't even write out this guy because it would look too ugly. But so you have a complicated Hamiltonian which you want to simulate. And what do we want to simulate? We wanted to simulate a tetraquark. And I will explain in a moment why we depict it like this. And to explain our tetraquark, I will explain it in the strong coupling limit first. I mean, in the simulation, it will look more complicated because we are in a general parameter regime and not necessarily in the strong coupling limit. But it's like for building our intuition, it's good to look in the strong coupling limit. So strong coupling limit means that these 2 terms of the Hamiltonian dominate, and you basically don't see the effect of the kinetic term Hamiltonian, because the kinetic Hamiltonian leads to a lot of pair creation, which really makes your whole state pretty complicated. So, ladies and gentlemen, this is the tetraquark and the strong coupling limit. So it has 4 particles. This is why it's called tetraquark. So it has 2 particles, 2 antiparticles, and it's a coherent, equally weighted superposition of having red anti-red plus green anti-green, or red anti-red and blue anti-blue, or green anti-green and blue anti-blue. So this is why we depicted it like this. This is a superposition of this, and this option. So it will look more complicated in other parameter regimes, but this is our strong coupling tetraquark. And if you were to use our translation table, you can easily write it down in spin language. Yeah. So in the end of the day, all our states will be just qubit states. So let us look at only 1 unit cell. Yeah. So not the entire lattice, but just 1 unit cell. In 1 unit cell, I go to the b = 0 subsector, where b is the baryon number, which is to say I want to look with you now only at states which have equal amount of matter and antimatter. Then there are only 4 options. So you can either have no particles, the bare vacuum. You can have 2 particles in a color neutral superposition, which we call meson. You can have 4 or you can have 6 particles. So this is a baryon, antibaryon, subaryonium. So that's all you can have in the strong coupling limit, and we can use this as a basis. So if we create a state, we can express it conveniently in this basis. Yeah. So, and I'm now depicting the energy spectrum in a parameter regime which is not in the strong coupling limit, but let's say we use this parameter regime, then you would have in the bottom the vacuum, then the meson, the tetraquark, and the baryonium. But so these sliders indicate, so it's not a, so this not so strong coupling baryonium is made mostly of the strong coupling baryonium, but it also has a fraction of tetraquark and vacuum in it. So it's mixes. And like if you vary your parameters, they can mix more and more and more, and they can even swap places. Now, so the tetraquark is now higher in energy, even though it has only 4 particles, and the baryonium is lower, even though it has 6. So it can get a little bit more complicated. And then what we do as a time evolution in our experiment that we performed is, as a proof of concept, we prepare an initial state, and as initial state, we take one that is in the strong coupling limit. So we start out from the baryonium in the strong coupling limit, and then, for instance, if you choose this parameter regime, you can just see it flipping and flopping around, exchanging energy with the tetraquark state. And for instance, if you were to use these parameter regimes, you would even have another frequency mixing in, and if you move farther away, you get more and more richer and more complicated time evolution. But basically, that's the experiment that we did. Yeah, so we did a Trotter protocol of this complicated encoded spin Hamiltonian, starting from a strong coupling eigenstate, switching on the Hamiltonian and seeing how it evolves and how the different states mix. So up to 8 Trotter steps meant up to 8 gates. We simplified the whole thing to be able to simulate it even with only 3 qubits, with some tricks, and then we observed the mean particle number over time. And the experiment was performed on the IBM quantum experience, and we employed some error mitigation techniques, which we call error self-mitigation, using randomized compiling, and I will be very happy to explain later on how this helped to clean up the Trotter evolution. So here are the results. Okay, this is a bit of a busy slide, so I will walk you through it. So if you look at the first row, I'm going into the easier parameter regime just to set the stage. And in the second row, it's a bit more complicated time evolution. So here we are in a parameter regime where basically the system only has one frequency, which is driving transitions between baryonium and the tetraquark. So if you look here, I think I even have it on the next slide. Yeah. So if you look here, it really has only one, like it's a plot which has only one frequency in it. And if you look at the violet purple line in the back, that's like really the exact, like if you do ED of the Hamiltonian, that's the exact result. But we do a trotterization. So even if the experiment was perfect, only because we do trotterization and don't do infinitely many steps, you would already have a deviation. So you can see this in the end, for instance. So the time was too long given our number of Trotter steps. So there's, even if the experiment is perfect, it would only go to the solid line, not to the dashed line. Yeah, and then, so these symbols are the experimental values where we use 2 Trotter steps for the early, like if you have short times where you need only 2 for intermediate and 6 for the long time. And so this matched our theory nicely. And so in the end of the day, we also did a Bayesian frequency extraction, basically showing if you had no ED, so basically if you didn't know the result, if you had only the quantum simulation and you would see the time evolution, you would do a Bayesian frequency extraction in order to get the in order to extract the frequencies, which in turn give you information about the energy spectrum. And that worked all out pretty nicely. And without going into any details here, I'm already summarizing this. So we did the time evolution of lattice gauge theory, and just a reminder, the motivation was like time evolutions are exactly one of the pockets where the traditional lattice gauge theory cannot go. And this was a proof of concept, which is one more step on the path to develop quantum protocols, but not just any quantum protocols, but specifically to simulate fundamental particle interactions. And so this is basically going the last step. We started from U1, also did SU2, and really arrived now at the gauge group that is relevant for QCD. And in case you wondered about the next step, so there is no shortage of next steps that have to be done. So something that is easy and straightforward is to add more flavors, so different quark types to your mix. Then it's of course of high importance to increase the dimensionality. So this was a 1D experiment, and we want to extend this to two-dimensional lattice gauge series. And of course, the big game is then to go to 3-dimension, because nature is 3-dimensional. And we have a separate research stream in which we use these exact methods, like these encoding methods, and show how it is extendable to 2 and 3 dimensions. But we practice with U1 first, like we practice with the abelian case to go to a higher dimension before we do it in the non-abelian case. Oh, and in principle here, there should be a line dividing before the third point, because the first 2 points, they are fairly clear. And the third point is so important, but it's a much larger quest, yeah? Because the ultimate quest is really to do a time evolution, which is not a benchmarking time evolution, but we want to do a time evolution which is really simulating physical dynamical quantities, where really experimentalists have questioned, oh, we need to know, so what is the time evolution here, like collisions, for instance. And this is of course one of the big quests in our subfield, like in our community, but it will take more time to develop those interesting time evolutions. And yeah, this directly is a gateway into my outlook. I was mentioning all the time these vast problem classes in particle physics that are insurmountable to the current methods, but are not a problem in principle for a quantum computer, so no roadblock inside. I talked about real-time evolutions all the time, but another very, very interesting problem is also if you have finite chemical potential, like if you have something that doesn't happen in vacuum, but if you have a physical process which happens in the background of matter, like say you have a neutron star, or you have like a big nucleus. And yeah, there's so much physics yet to be explored. It's one of my favorite pictures, no, because this is a chemical potential here. And so basically this slab is where traditional methods cannot go. Yeah, can go. This blue slab is where traditional methods can go. And all this physics is inaccessible. And this is where we could go if we had a quantum computer. And like there are experiments, there are hypotheses, like there's so much physics going on. And it would even touch several different fields. No, it would touch particle physics, nuclear physics, cosmology, astrophysics, even condensed matter physics. Yeah, so I think it's really worth the quest to develop this knowledge or ability to teach quantum computers how to help us here. So the ultimate vision, from my point of view, is actually a hybrid computing infrastructure where we have the regular computers and quantum coprocessors that help with simulations. And of course, better simulation abilities will pave the way then to new discoveries. And there's then a lot of unexplored territory ahead. And if someone is enticed to follow us on this quest, so we have positions available, and you can just drop me an email and contact me. And with this, I warmly thank our sponsors, without whom this would not have been possible. And I thank you for your time.
Yeah, thank you for